Okay, great.
While everybody's still filing in here, we'll wait just a minute or two before we get started to let the room fill up, and we'll get started about maybe 2 after the top of the hour. Right, I think we've reached a critical mass here. So welcome to our ASABE member hour, highlighting the AE50 and Davidson Prize award-winning product Iyris from RedSea. I'm Chuck Roth. I'll be your host today. And a couple things as a background. First, ASABE member hours were started as a mechanism for the wider engineering community to learn, connect, and grow through presentations such as this one that we'll have today. The 2 awards that will be that have been presented to the RedSea Corporation is the AE50 and the Davidson Prize. So AE50 award winners include machines, systems, components, software, and services that are ranked high in innovation, significant in engineering advancement, and impact for the markets that they serve. The Davidson Prize winners are a subset of those AE50 award winners and is named for J.B. Davidson, the father of the modern agricultural engineering. Dr. Davidson was the first person to combine the great professions of agriculture and engineering and helped form the ASABE Society. He gives a nod to the storied past of agricultural engineering and pays homage to those engineers like J.B. Davidson who aspire to find a better way. So for today's member hour, a few ground rules. If you have questions, you can feel free to place them in the chat during the presentation. And we'll cover those first as we have a Q&A segment. And then towards the end of the Q&A, if there's some time left, we may be able to open it up for verbal questions. So please don't hesitate to drop those questions into the chat. I'll monitor that and relay those over to our presenter as that Q&A time opens up. And then also this meeting is being recorded. You got that notification probably already, and it'll be available for later viewing via the ASABE website. So today we're going to be hearing from Daniel Bryant, who's Chief Technology Officer of RedSea, regarding their heat blocking greenhouse roof named Iyris. I could go on to describe the solution, but I think Daniel can do a much better job. So go ahead, Daniel.
Yeah, thanks, Chuck. I just want to say I'm honestly really humbled and honored to be here talking to you today about Iyris. I'm CTO of RedSea now, but I was actually one of the original team who developed the innovation that I'll explain to you today, and some of the journey of how we got there. And it was always one of my dreams, really, to take something from the lab to a commercial reality. And honestly, the AE50 and Davidson Prize is a recognition of the achievement of that dream. So I'm excited to share this with you today. So first of all, I'm Dr. Daniel Bryant. I'm the CTO of RedSea. And my route into agriculture is really, I'm a material scientist and engineer. spent all my career in new materials for solar energy. So you can probably see where this is going, assuming as we're talking about innovative roofs. And I did my PhD, was lucky to be sponsored by BASF and Tata Steel. And that's me in the middle there on the left, looking slightly fresher faced with the team on one of the first fully printed solar cells on metal. And then I went to Imperial College London, and then I came to King Abdullah University in Science and Technology in Saudi Arabia, where I'm based right now. And that's where we really started this innovation and did all the startup accelerators, as you can see in the bottom right there. So I'll just go into why and about our company, and then I'll jump into the innovation. So, I mean, one of the big things that we always set out to tackle was the change in climate. So anytime you open the news at the moment, you always see some things going a bit crazy or unusual in a different country. And these kind of big changes and increase in heat waves, droughts, are something that we sort of, how can we make our food system more resilient? And really we started in the regions that are where it's already very hot and hard to grow. So 1.5 billion people live in regions that we described as water scarce already. And these are areas which are really around that equatorial region that are categorized by high solar installation, high sunlight, which is great on the one hand, because we've got 43% of that sunlight for the plants and for growth. But the remaining 52%, which is one of the things we try and tackle, is the invisible part, the near infrared part of the spectrum, which is really causing the heating. And that's sort of everything that we do comes down to this heating. And again, if you look at greenhouses in all these regions, actually they're powerhouses of the food producers. So a lot of fresh produce from Mexico to USA. Europe is supplied a lot by Spain and Morocco. And where we are, GCC, is also supplied by Egypt and Jordan. And these are often simpler structures. They're usually what's called covered agriculture rather than greenhouses. So this is where we kind of sit as a company. And we were founded really with that in mind and trying to break this food, water, energy nexus by two professors, Mark Tester and Daria Baran, and our CEO, Dr. Ryan, who I believe spoke at the last event, who was an agricultural engineer, mainly focused on water and the use of water. And we've grown to 50 people, many nationalities, and I'm honestly surrounded by highly intelligent people all day. So I'm very lucky to have such an amazing team in our company now. And we've grown and we established in only 5 years. And again, I want to say the Davidson Prize and the AE50 are very meaningful to us because it's one of our first prizes for products. We won a lot of prizes for being a company, for doing a startup, for innovation, for everything. But actually, these prizes were the first thing as a recognition of commercial products. So it'll always have a very special place for us. And the final comment on the wider company is we have Iyris, which we're talking about today, but we also have technology development called Volcano on genetics, resilient genetics, which are salt and heat tolerant. And we're also working on sensing and data that's especially designed for harsh climates and hot climates. So today, focus is all on Iyris and the development that got us here. So a bit of background in where we started and where we came from. So it actually started in the labs of Professor Daria Baran. And again, that's me in the bottom left working on these new technologies. So this was the idea of how do you make solar cells transparent? And with a solar cell, you still need something, you always need something to absorb energy and turn that energy into electricity fundamentally. So you still need something that absorbs. So a way to make a solar cell transparent, in this case, they were called organic solar cells. You try and shift that absorption into the near infrared region. And this is what we were focused on, is shifting that absorption of the solar energy into the near infrared region to increase transparency of your solar cell. And if you know this graph, or if you don't, this is a graph originally done by NREL. It's a global average of sunlight hitting the Earth's surface at every different wavelength. And you can see, obviously, you've got the visible part of the spectrum is the highest peak, but actually the area to the left of the red, so beyond 750 nanometers, is actually, that's where the area under that curve is 54% of your energy. So there's a huge amount of energy there to work on and to try and get rid of. And one of our early conversations was with Ryan, our CEO, and we started saying, we've got this technology, it's NIR absorbing, it's highly transparent in the PAR, and it can produce electricity. And he said, no. If you can just give me NIR absorbing and highly transparent in the PAR, this solves all the problems of desert horticulture, because you then can decrease your solar load within your greenhouse. And this is desperately what we're always fighting against. So we went away to the lab, and literally this is around 2018, and early 2019, and we started developing materials that basically could do this. So it had a high transparency and a high NIR blocking, and the material on the right is actually, I dug out, because when we won the Davidson Prize, I actually went back and found this picture, because this is one of the first prototypes we ever made that successfully did this. And I was like, here's where it all started. So this is actually kind of where it started in the lab. And this is it. So if you look at this orange curve then compared to the blue, and then the green would be a glass, for example, or you could have a polyethylene cover that would be very similar. You would drop a bit of transmission all the way along the spectrum. And you compare that to our materials. You're talking about keeping your PAR as high as possible. There's a small penalty, but you're still very high transmission. And then you drop down as fast as you can, and then you keep your NIR low. And then what you can start to do with this is you can start to tune where you drop off, and you can start to tune how much you're blocking. So this was kind of one of the very first materials that we developed. And I would point out, at this point, we were thinking of coating. So we were thinking of something you could maybe paint on, or something that could be retrofitted to greenhouses. And we actually went away and we tested this. This is the university here. We have a big research greenhouse, and we went and tested what our new coatings would do in greenhouses. And when I say greenhouses, these are the greenhouses we built at that time. We're talking about 50 by 50 centimeters squared, and coating a material on the roof and growing 4 lettuce inside. So kind of funny to be looking back now from where we came, but we definitely had to start somewhere. And it's kind of a good acid test that we always do now, even in the company. It's like, make something on a bench, see if it works in principle. And actually, like, what we saw was these spiky looking graphs are because there was shading throughout the day, but as you go from morning to night, you can see that your broadband luminosity, so roughly equating to your PAR, remains similar between a coated and a non-coated small test greenhouse, and your near infrared luminosity was altered, so it was decreased. And really, this was kind of like promising enough for us to start taking these materials sort of forward even more. And on the mini greenhouses, actually, it proves the fundamental effect. And I kept this in here because it's the same effect. It doesn't matter if it's 50 centimeters squared or 50 hectares. It's basically, all we're doing is reducing the solar load that comes into the greenhouse and reducing the amount of work that has to be done to remove that solar load. So whether that's you just use less water, you use less cooling systems, or however you remove that solar load, it doesn't matter if it's small or big, it's the same principle. And so what we saw was actually you can keep the peak temperature the same, but when the sun starts to go, there's actually the one in the uncoated the fans stay on, and so you consume more energy. So over time you have this widening of energy, and we found about a 25% energy difference even at this kind of rough and ready early prototype stage. And again, this was enough to take this forward. And of course, the sample size of 2 times 4 lettuce, which was you know, not exactly the most scientific we've ever done, but again, the fact we weren't seeing huge differences and changes was enough to take this forward. And then COVID happened. So actually then, you know, we hit a wall because we couldn't get to the labs and we couldn't do anything. And so this whole thing around, as we all know, around 2020 stopped. And I just want to make a comment on COVID because it was a big changer for our business. Where we are in the Middle East, it's 80 plus, 90 in some countries, imported food. So big imports. And before COVID, food security in these regions meant having multiple sources. So having multiple other countries that if you know, war broke out in one, you could still have another country to pull on. And COVID came and changed that all up because then it was like, okay, what if there's no sources to pull from? So we as a company went from interesting company trying to save water, trying to you know grow in the Middle East, eco-friendly, to having conversation with defense ministers because how do we feed our people if we can't get any food in? So this really kind of shaped our business, and after COVID accelerated it even further. And during COVID and towards the end, we realized that we as a company, and we made the conscious decision, we wanted to have the biggest impact on the world. And by having the biggest impact, we needed to be in kind of the most greenhouses. And when you look at a greenhouse, you can tell from my accent, I'm from the UK, we commonly think of glass houses, or greenhouse in the traditional sense. But these are common in colder climates, and of course the Netherlands is a major player here, but the vast majority, 90+%, is in the hotter regions, even Mediterranean, Southern Europe's, North America's, and they're pretty much all plastic in one form or another. So we realized we suddenly had to be not a coating anymore, but we had to start thinking of ourselves of embedded in the plastic. And actually, this was the catalyst, and this was the accelerator for this whole project and this whole product. Because once we could get our materials compatible with polymer, and I'll explain this chain in a minute, but once we could get our materials compatible with polymers, we could very quickly go from a raw material to a master batch, to extrusion, to finished product with commercial partners at scale very quickly. And this is, if anyone doesn't know, essentially, if you look at any plastic, you've probably got a keyboard or a mouse, or your computer frame is a piece of colored plastic. And how that plastic got colored, someone took probably the color black, and they concentrated it into a master batch. So they put a high concentration into a pellet, and this is a highly concentrated pellet, and that's called a master batch of color. And then you put that master batch into your extrusion, and you mix that with the bulk polymer, and then so it becomes less concentrated, and then you extrude that, or injection mold, or whatever you want to do, into your finished product. So as soon as we got something that everyone could think of as just a colorant, just a pigment, or just a dye, and just a master batch, then actually everyone was happy to talk to us, and we could go from, you know, the grams of the lab up to the tons, the kilos to the tons, and to the kind of hectares, honestly, incredibly quickly. So this was one of the kind of breakthrough moments for us. And this is what we call Iyris. This is, we think of the Iyris as the kind of technology here, and Second Sky as a kind of finished product, and Second Sky specifically on the near infrared blocking. Going into polymers as well has many advantages, because the big thing is that we don't change the film really in any way apart from optically, no more than, you know, your red colors or your blue colors change it just visually. We just happen to operate in the near infrared. So all things like your mechanical strengths and your durability, your thermic effects, lifetimes, and really importantly for the farmer and the end user, your installation. So this is a like-for-like replacement. It's the look, the same feel, the same texture, same density, everything the same as your normal roof. It just has an optical effect in here that does all the work. and of course, actually embedding our material into the polymer has durability enhancements as well. And what does it look like as a finished product? So this is a transmission graph now, a UV-vis transmission graph. So going from 0 as an opaque up to 100% as opaque as air. And then a normal polyethylene film is this sort of lightish one at the top. That would be our reference guide. And you can see that by adding different concentrations, so this is just adding more into the film, we're getting a higher NIR blocking. And we can vary this around. And really the interesting thing that we're finding now is, broadly speaking, the closer to the equator or the hotter the region, you probably want more blocking because you usually have lots of BAR, so you don't mind the sacrifice here, but you really want this because you have lots of temperature buildup. But we're finding actually, even in regions such as Southern Europe, in certain crops such as even peppers, you can go quite aggressive and you don't get any penalty and you start to get some upsides. So this is kind of the main effect that we're seeing in our films here, is this near infrared blocking in this region. And then again, one of the beauties of getting into polymers is kind of once you got into one polymer, it's not too hard to leap into all the others. There's some tweaks, but it's really not a full redesign. So you can go from shade nets, and shade nets are a huge area of the market that are very diverse in their usage. Everything from keeping birds out right through to literally shading, right through to trying to keep insects inside or outside, and everything in between. So shade nets is a whole subsect in itself, but they're almost all made of high density polyethylene with some polypropylenes in there as well. And then you've got your polyethylene, the low density polyethylenes mixed with various other polymers, are what you would think of as your stretch polyfilm. And they're really the two big workhorses of the market here. And then you've got polycarbonate as well, makes it up. And then you have slightly more niche applications such as PMMA, acrylic. And they all have different lifetimes. So how often this is being replaced. And this is sort of another impact from a commercial point of view, which was another good way for us, is that we had a chance to intercept a roof, because every 3 years that roof is being replaced anyway. So wouldn't you want to replace that with something that can potentially save you water? That's kind of the mindset we're starting to get people in. So in terms of performance now that we've scaled this technology up, it's been working, it's on a larger scale. Where we initially designed and developed this for was hot climates, and most of our hot climates are cooled. They're cooled by swamp coolers, pad and fan systems, where you evaporate water on a porous pad, and you pull that through with a fan or push that through into your greenhouse. And what we thought about is, let's include the roof here, and you simply just have lower solar load in your greenhouse. So simply you can reduce the amount of energy and water that you would have to put in to remove that solar load, while still keeping all the PAR high for your greenhouse. But then actually what we also found was, of course, this is going to work for naturally ventilated greenhouses, so tunnels, polytunnels, things under shade nets, something where you're not doing any mechanical work to keep that greenhouse cool. And there you have temperature reductions. So we conservatively say 3 to 5, although we'll see there's even some higher temperature reductions. And importantly, we're not just talking about air, we're talking about plants, and we're talking about soils as well. So this is really impactful, as we'll see. And then on the other end of the spectrum, so down here, like we had in high production greenhouses, we have this slightly counterintuitive effect where we actually get a yield enhancement in certain cases due to a light increase. So this is just from the need to decrease shading. So you don't have to pull a shade screen as often, or you don't have to chalk as often, or you don't have to chalk as early in your season. You could delay it a month. So your yearly light integral, the amount of light you get in that greenhouse over a year, can actually increase. And we had all these benefits: higher light, extended season, healthier crops, cooling, water saving, of course. And then when we get down here, actually, some of the more interesting things, and going back to my earlier slides when we were literally developing this in the lab, we kind of could never think that we're now looking at the productivity of the workers, because workers are more productive behind these greenhouses because they're simply getting less radiation on their head. And when we built our latest greenhouse, which is in the picture down here in the UAE, the workers used to literally fight of who got to work under the Iyris roof, because it was much cooler for the poor guys working in the high temperature. And now we're actually doing all these things where we're tracking labor, and we're starting to see, like, does this have a health benefit for the workers? Which again is kind of really crazy for me to see this when you think about, like, I'm a material scientist, so I wanted to create something that had an engineering effect, and now we're having social. So in the Middle East, we're in the UAE. This is our own test facility, and so we can run it as an experiment and however we want. It's in Al Ain, which is in the UAE, which is over here, and it's actually a bit inland, so it's not quite as humid as the rest of the UAE, but it is still up there in terms of temperatures, 40 pluses regularly in the summer. And it's all a pad and fan, which is the commonest type in these kind of regions. And it's all a multi-wall polycarbonate structure. The thing I want to just highlight here, slightly off topic for Iyris, this top left picture, you can see is it's actually fodder. And what we do with this greenhouse as well, we use any runoff of the water from the swamp coolers and also from the irrigation systems, and we dump it to this fodder out here, which is then grown on essentially wastewater, which would have otherwise got dumped or pumped back into the ground or sort of wherever it came from, to have a second chance to grow fodder for animals, which is a big thing, especially in the Middle East. So we have all sorts of things going on in this greenhouse, but mainly the one we're obviously going to talk about is an A/B comparison with the Iyris roof. And this is one of the big effects that we see here. If we look at these two graphs on the left, the top one in red is a control greenhouse. So what you see, you have your pad on one side, and you have water coming. You have water running over that pad, and you have air coming in. And really, what happens then is the inlet temperature is roughly equal. So your temperature coming off your pad is an effect of the outside temperature and the amount of air you're pulling through. But as it goes through the greenhouse, so if you take these lines and you move upwards, that's really your gradient across your greenhouse, so your gradient from your inlet to your outlet. So when you don't have Iyris in and you have the pad and fan system going, you're actually getting a delta from your inlet, which seems quite nice, around the 24s, and it's getting up to the higher 30s, so you have quite an uneven crop going through your greenhouse. And in Iyris, we have a much lower delta, basically. So we can decrease that delta, and then that has all sorts of impacts. I mean, one of them is obviously we don't have to use the fans quite as less if we want it to be equal, or we have a more even greenhouse and a more even growth, which all the agronomists then get really happy because they don't have to work so hard to keep all the plants balanced. But also we could, in theory, do engineering changes to the greenhouse, like extending the greenhouse, so extending the rows, which makes workers more efficient because they're in longer rows. These greenhouses are all limited to about 30 meters because of this effect, that your air just heats up so much as it goes through the greenhouse on your hottest days. And again, even in sort of Junes, this is in July, and in Junes we get this delta depending on what's coming in. And one of the key takeaways here is the kind of striking decrease in water in regions where water is kind of a precious commodity, or a hard-earned commodity in terms of energy use. And we can save about 40% less water for cooling, while only really sacrificing about 8% in the overall DLI. And the other interesting thing is these are all in hydroponics in this greenhouse, but we're still having a water saving, basically on our irrigation water. So the impact on the irrigation water is good, but obviously in things like soils, that even increases further if you're in soil greenhouses. And our yields, we did actually have some changes in yield, but what we were trying to aim for was actually sort of a very similar yield. So we got an increase, although by the time we'd finished the whole season, we actually wanted to average everything out. We actually tried to keep everything in terms of yield very similar, and we went for things like water saving. So you can run your greenhouse and you can start to manage your greenhouse in very different ways. So then I want to just do two more examples here. So one is in Europe, in our site in Spain with strawberries. And I really wanted to show this one because I find it one of the most interesting ones that, again, we never thought we'd kind of be targeting places where it's traditionally good climates to grow, like Spain. But we are stretching further and further north. And I would say, as a side comment, we are actually doing installations now in the United Kingdom, where I'm from, which is always a hilarious thing to me, growing up in a cold, very rainy country, that we're doing heat blocking and water saving films. But so kind of this is the effects that we're seeing and the impact on farmers with the current climate. So in Spain, this was 2 tunnels side by side. So we actually, if you designed it as an experiment, you'd say it was a non-perfect design because you'd like perfectly isolated tunnels. But what we saw was the air temperature the air could mix. So the air temperature was never going to be much different. And this was all in strawberries. And what we saw was, as I say, the air temperature is approximately similar within range of each other day by day, which we expected because there's just full mixing of air between these 2 tunnels here. The one interesting thing, the unexpected thing, is the guys said on this greenhouse, even though it wasn't the actual side is the regular, but because it was located next to you can see this nice blue, that's our plastic tunnel, they didn't have to pull the sides up and down as much for ventilation. And when you look at how many hectares, it's actually over 1,000 hectares, 2,000 acres worth of farm, you can kind of imagine the labor to go around and pull these ones up every time it gets a bit hot. So the farmer was very, very interested in this labor saving and this kind of human element, and we're investigating that now. But what the impact that we saw on the plants was, taking it back to basics, plants are essentially water bodies, which water is quite good at absorbing the near infrared. And so we saw the leaf temperature had a big difference here. So a few degrees between our different leaf temperatures, or the maximums and average. And actually there is a slight decrease in the in-canopy temperature. And of course, the fruits themselves will absorb radiation. They are essentially water bodies of water as well. And so again, we see these kind of deltas between the actual fruit itself. And one of the most important effects that we saw was the soil temperatures. So this is all grown in soil, strawberries grown in soil. And the PAR, there was a slight change, of course, that visible light penalty. But the soil temperatures increased, and you have your increase kind of in the evening when the sun is going down. And this is how the land heats up throughout the day, of course. And what we saw was basically the change in PAR is somewhere here on the curves, and strawberries aren't, the relatively lower light crop anyway, so there wasn't going to be a big impact on yield. But of course, when the sun is going down, the plants have to keep themselves warm by consuming their sugars. And so having a warmer soil temperature when you're starting to lose your main energy source of the sun to keep yourself cool is actually going to have an impact on your strawberries. And what we saw was, rather interestingly, we saw an increase, although the overall yield was almost identical. What we saw was a flip in terms of they had a higher marketable yield of their first grade strawberries. And the really big impact of this comes in the fact that the price you can demand for a higher quality is 5 times. So again, just this kind of, I always take it back. We did a simple material science optical change concept, and now we're having this kind of real world impact. And this is some of the beauty of this innovation, really, is that now we're seeing actual commercial benefits and commercial gains for the farmer out of these materials. And of course, overall, you get about a 9% increase in revenue, but very important to notice that 9% increase in revenue is without increasing your OPEX at all. So it's essentially strapped straight onto your bottom line there, because what you would normally, same strawberries, you didn't change anything about your fertilization or anything. You can have this increase in your profit, essentially. Final one then, actually. So North America site, and we're doing some work now in Arizona. So this is we had the kind of tomatoes in the Middle East, and we were thinking about strawberries and soft fruits in Europe. And this is actually where we trialed in seedlings, so in a nursery. So not only how does this affect full production and plant it once you've planted them at a seedling maturity, but how does this affect seeds as they are developing? So this is in Arizona. Of course, we know a similarly hot and dry climates. And so again, we put this roof on in the bottom right, and we wanted to measure what's the quality of the seedlings. This is kind of unique as well, because now it's a 2-layer polyethylene, where you have 2 layers to have the bubble in between your greenhouse, so that you can improve your insulation of the greenhouse. Really helps, obviously, when you have that hot, cold temperature changes in places where the nighttime temperatures get cold, very cold as well. And yeah, we basically measured the plants. Again, slight change in photosynthesis. This isn't too impactful because the plants are obviously very, very small anyway. And the greenhouse temperature changed. And one of the big interesting things that we saw here was that actually the root development has been basically more prolific in everything, and you can see the kind of difference between the plants here. And I don't know if the video will work, and I'll try and do the sound, unless anyone speaks very good Spanish. But essentially, this is our nursery. This is one of our growers, Paco, and he's explaining how these are amazing roots, and how the uniformity actually was even increased in the seedlings, which is again a really big thing for the nursery. So the uniformities of all the plants, and if anyone speaks Spanish sign language, they're saying they're very, very good plants, essentially. So this is where we're at. So the final slide I have is on some future developments, because this is something we're working on now, and actually I'm very proud of, because of course I've talked everything about how we can impact the current food system, how we can make our current food system. We're not trying to reinvent how we grow, and we're coming along with a different way of growing everything. What we're taking is the current way we grow in this world and trying to improve it. And that's really comes down to things like water saving, or how can you grow less, or how can you grow more with less, and that kind of comes back to a sustainability drive. However, then I always talk about plastic, and then you could kind of say, well, you say you're sustainable, but aren't you just selling loads of plastic? So this is really where our next innovation we've been coming from, and that's working on that bulk material. So we've been working with SABIC. SABIC, obviously, big Saudi company, big worldwide, one of the biggest chemical companies, also the world's biggest polyethylene producer. But they have been investing heavily, and they have a very big initiative called True Circle, which is trying to make plastics from renewable feedstocks. So these are either from biorenewable feedstocks or chemically recycled feedstock. So pyrolysis oil feedstock. So something that you can put round the circle again, or comes from a non-human food competitive source like waste, like tall oil, or from trees, or waste fish oil. So they've produced some of the world's first polyethylene that comes from renewable feedstock material. And we are what's called ISCC Plus certified materials provider. And we're working with another local company who's also ISCC Plus, so International Sustainability and Carbon Certification. You have to meet, it's like getting certified. We've gone through the process, SABIC and NAPCO have, to get ourselves certified so that we are certified kind of sustainable. And we're producing the world's first renewable greenhouse roof, which is ISCC certified. So not only can we really have that sustainable features, like sustainable impact on the greenhouse, we can start to say the material is sustainable. And then going even further, then we're adding a duty of care into the recycling. So every roof that we install, what happens at the end of life, and we're working with pipe manufacturers if we need to mechanically recycle this. So thank you very much for staying on and listening. I hope it was enjoyable and took you down some of the journey to sweat and tears to get to where we are, and some of the impact that we never thought possible. And thank you again to for the AE50 and the Davidson Prize. And yeah, happy to open for questions. I think we're going for the chat first, right, Chuck?
Yeah, we'll step on through those. I would say first, congratulations to you, and thank you for sharing today. We'll launch into those questions. The first one that I had was, as you look at some of those longer lifespan materials, I just snagged acrylic as one of those that had the longer lifespan. Have you seen or do you expect to see any reduction in the effectiveness of the infrared, near infrared blocking over time?
Yeah, so Chuck, I mean, if I can go on, it almost seems like a setup, because I had this, but to the audience, I promise we didn't have this prepared. So actually, it's a really, really good question, is what's the effectiveness of the additive of the material over time? And so when you're talking about a 3-year lifetime material, you only have to last 3 years, okay? So that's doable. But yeah, right, in the PMMA, so actually we've done we're still doing, and we're doing lots of weathering tests on these, and we're seeing, we do simulated, so actually this is how you put solar cells under stress as well, simulated sunlight. And what we can see over the equivalent of about 3.4 years, we're only seeing a 5% change in material. So this takes us on, I mean, if you think about T80, then we're getting to 12s. Basically, it's acceptable, even over the PMMA's lifetime. I think one of the important things as well, which is nice, actually, the more aged these materials go, the more transparent they go. So they don't kind of go a darker color, they actually go just more transparent. So at least it always goes in the right direction, even if it's degrading. Okay, you lose the effect, but you're not muddying or decreasing the light transmission in your roof. Yeah. So that's a kind of important thing. Like say for your 3 years, 5 years, even 10 years, it's really not degrading too much, which is we're happy with. Yeah. Thanks. You're on mute, Chuck.
Oh yeah, no, I was just saying that's awesome. Thank you. So the next question was earlier on in the presentation, and so you hadn't started talking about it yet. So the question was, does the coating complicate end-of-life disposal or recycling? And it seems like you kind of answered that question. I don't know any more to add in that regard.
Yeah, I mean, it's worth to insert with, it's not toxic materials, it's not heavy metals, we're not talking about PFAs or anything you hear about in the news. So there's nothing really to worry about, especially in terms of like initial toxicity or leaching or really anything at end of life. Of course, the additive itself is quite a very low concentration. I mean even low concentrations are reported if you're talking about heavy metals, but we're not. So we are quite low, and yeah, it's actually a good question because it's something that came up when we talked to people like ASABE about this true circle material. Like, is it impacting how we recycle this? The sort of answer is no. What you do with it at the end of life is really dependent on what kind of happened in its life rather than our additive. It's how degraded did it get? Can we put that into, like we're working with a pipe extruder to grind this up and put it into pipes. So no, and like I say, it's kind of it's almost the same as a pigment and a dye. And so no, your plastic gets treated like something that's colored, which most plastic actually is. Yeah. Actually, the next one, what was the air temperature in the AZ greenhouse? I think you actually see it, and we see it here. There was actually a 6 Fahrenheit. Yeah, sorry for my metric numbers throughout this, but we actually did this one 6 degrees Fahrenheit, despite both greenhouses. We kind of had the same target temperatures in both of these. There was fans, so there was ventilation, but even still, this kind of shows you that the fan and the cooling system probably wasn't spec'd high enough, because you're still seeing too high temperature, which probably pretty much means the fans couldn't kind of keep up. Yeah. I can actually keep going. Are you able to grow tomatoes year round in Saudi Arabia? Does it get too hot? Yeah, great question. So it depends on well, we would like to think with our technology that it makes it possible, including all our technology stack, the roof and the roots. And you definitely can. There are companies out here that grow year round. So it is possible. The common market out here, the main season is our winter, which is usually kind of around the high 20 degrees Celsius, mid to high 20 degrees Celsius. And that's when most growers grow, just because it starts to get harder in the summer. The big important thing there is actually around things like pricing as well. So if you are able to grow in the summer, if you kind of, it's one of the logic behind investing in technology, and even sort of technologies such as ours, that your price you can command in the summer becomes much higher, obviously, because you're growing at a time when local growers honestly just don't want to, because it comes with a lot of not only abiotic pressures, but also biotic pressures. The chance of molds go up. So yeah, it's of course possible. There are people doing it, but there's still a choice in there. Yeah. Thank you. Well, thanks everyone for joining. Does this change the temperature of the material itself? I think is the next question. Yeah, so the answer is yeah. So I didn't really go into it, but we absorb, we don't reflect, which is a very important point. And actually, when we started, everyone told us focus on reflection of the near infrared, not absorption. And then what we've actually come to realize is that absorption is better, because with reflection and your leaves and the ground and everything, and your greenhouse will actually do a lot of near infrared reflection anyway. So anything that's not absorbed might reflect from your greenhouse back to your roof, and if your roof is then reflecting near infrared back down, it's sort of got another chance to trap in. Whereas ours is at least absorbing in the way up. And thermodynamics was nice to us because the greenhouse roof is at the top, And so we're trapping the heat at the top, and heat is always going upwards. So the roof of the greenhouse will preferentially get hot. Your energy gets trapped basically at the top of the greenhouse, and then but at least you can exchange with the outside air, and that's why we think we're seeing these cooling effects. And it's a great question, because honestly, when we did very first designs, we were kind of like, we need to stress test if this is just going to warm the greenhouse itself preferentially. But as I say, luckily you kind of trap all that thermal energy at the roof, and it's carried away basically with the outside air. I would also say the other thing is we don't change thermic properties. You might have heard thermic properties, like the literal greenhouse effect in the material. So at nighttime, trapping the heat in. We work in the near infrared range, not the mid. That's all the mid infrared range. So completely different parts of the spectrum. And actually, we kind of just don't affect that at all. So if a material is already what's called thermic, if it's already good at trapping, it remains good at trapping. And actually, a lot of the European climates still want that, because they want to keep it warm at night. But yeah, so yep, and that's you. And I think it's, well, thank you everyone. I think thanks for listening, and thanks for joining us. I don't see any more questions unless I missed any. Chuck?
You didn't miss any. Any questions that came up, somebody would like to come off mute and ask? You're more than welcome to now.
Chuck and Daniel, yeah, hey, great job. Curious, does the material, the physical characteristics of it change much over time? Does it become more brittle? And also wondering if, I can see on one hand, why would you guys test it, but how it necessarily would react in colder climates?
Yeah, okay. So on the material so far, and really we are rigorously testing, or have been rigorously testing a lot of different types of material. If we take, say, polyethylene and even polycarbonate as an example, the reason they remove these materials is because of it's not really the physical properties, it's the optical properties. So it's hazing of the polyethylene itself, which is pretty much photooxidation caused by usually sulfur from things like pesticides reacting with a radical that's come from UV. So it's essentially a UV-led degradation of the polyethylene. And we don't have an impact on that. I mean, the roof, in terms of mechanical properties, even a polyethylene roof could stay good for 8 years, but it's just milky, and it's cost effective to replace it. Some of these guys are replacing once every year, like every season, but usually 2 to 3 years is about when you replace. So we don't have an impact, and as I say, always worth to bear in mind, we're actually a very, very low concentration, because we're an optical effect. So, and that was one of the beauties of this material. We're not talking about having to put too much in to change just optical. And polycarbonates are actually the same. They're yellow for a different process, but basically lose transmission. And the PMMAs that we kind of it's such a hardy material. We just have to blast it for so long, and we're still blasting it, and we're not seeing any big change in that either. So again, we just kind of say that we are neutral in terms of things like lifetime, things like mechanical properties. We just try and say, the film you've always bought, and you know how it operates in terms of lifetime and everything, it's going to do the same. We just change that optical. And in the terms of would we use it in northern climates? I mean, I wasn't joking when I said we put it in the UK, because of the UK season is actually August, and they get up, they got up to 40 degrees in their greenhouse, and believe it or not, places like the UK even have water saving restrictions in the summer. Winter's a different story, but in the summer, actually water gets more scarce. So we are more northerly and more southerly when we're in South Africa as well, and we've got stuff in Chile. So we're more away from the equator than honestly I could ever predict. And we are actually looking at innovations now of how we can possibly, and this is a look behind the curtain, how we can possibly do something with that energy in maybe colder climates, because we are trapping the energy. Can we start to use that energy for heat for the greenhouses? So yeah, it is something. Funnily enough, it's something we are actually looking at. There's more northern and southern climates. Yeah.
Excellent. Thank you.
Thank you. Thank you so much. There's any more questions? I mean, was happy to take them, or you can always email me, of course. My email shared, and then but Chuck, I think you want to take a few minutes to wrap up and share some announcements.
Yeah, just again wanted to say thanks for your time today, Daniel. Awesome product. It's really innovative. I had not heard of it before, and so different industry. So it was really exciting to hear and hear the change that you're affecting around the globe already. So that's awesome to hear.
Yeah, thanks so much. Thank you.
So yeah, just a couple of things. Also wanted to say thanks to Sarah Rodriguez is on, and the rest of ASABE staff, as well as several others that help make all of our member hours a reality. One note, if you or someone in your network has a new product, service, or system that they brought to the market this past year, consider nominating it for an AE50 award. The deadline is September 25th, so time is of the essence, but there is still time to get those AE50 award nominations in. If you are looking for that, you can do a simple search for ASABE AE50, and you'll undoubtedly get connected to where you need to be to submit that nomination. Our next member hour, I believe, is October 11th, and that's going to kick off a series on modernizing African agri-food systems, and it's titled An Introduction to the Alliance for Modernizing those African agri-food systems. And again, thanks for your time today and your participation, and look forward to hosting you again at some of our future events.
Thanks so much, Daniel.
Yes, thank you. Thank you, everyone. Thank you.
Thank you.